In this video, we're going to look at the limits of sequences. So we want to be able to determine if a sequence converges or diverges. If it's convergent, we want to be able to find the limit, and then I want to be able to look at the connection between the limit of the sequence and the horizontal asymptote. So when we talk about the end behavior of a sequence, we're looking at what happens to the terms of the sequence as the position gets very, very large. So graphically, what we're doing is looking at what happens as we go to the right forever. So if I graph the sequence and I look at what happens as we go out to the right forever, are my terms getting really, really large? Are my terms getting really, really small? Are my terms becoming almost constant? So what kind of behavior is happening as we do that? Basically, that end behavior can be classified into one of two things. Every sequence is either convergent or divergent. A divergent sequence is a sequence that does not approach a particular value. So basically, it could go up forever, or it could go down forever, or possibly it could be alternating between two values, or it could be alternating between going up forever and down forever, or doing some other kind of chaotic behavior. Graphically, we could be looking at something like an exponential sequence, so the graph's going up forever. Or perhaps we're looking at some kind of maybe a rational function where we have an asymptote, and then maybe this one's going down forever. Additionally, we could have a sequence that is not a constant function and is just kind of jumping back and forth between positive and negative values. So all of those would be considered sequences which are divergent. So the alternative is that the sequence is convergent, so it's going to approach a particular value. And this means also that it's going to have a horizontal asymptote. So graphically, a sequence that is going to look like a convergent sequence maybe would be something like this, where we have a horizontal asymptote here that we're not going to cross. So when I have a convergent sequence, then my sequence has what we call the limit. So the limit of that sequence is going to tell us about the behavior as our terms get really, really large. And again, if the sequence has a limit, which means it's convergent, then the graph is actually going to show a horizontal asymptote. Okay, so here's an example. We want to find the limit of the sequence and tell if it's convergent or divergent. So the first thing that we want to do is look at our sequence. We have 1 over 1, 1 over 2, 1 over 3, 1 over 4. So this is my first term, my second term, my third term, my fourth term, and then this is what we call our nth term. So I have 1 over 1, 1 over 2, 1 over 3, 1 over 4, so my nth term is 1 over n. So this is my explicit formula. So when I have an explicit formula, I want to just graph that. So we're going to graph this explicit formula, and we're going to get the picture that we have over here. So to determine if it's convergent or divergent, we're going to look at what's happening as we go out to the right forever, and we can see here that we're becoming almost a constant value. So we're leveling off to a horizontal asymptote. So this is convergent. So out here we are approaching a horizontal asymptote of y equals 0. So again, when we have that horizontal asymptote, then that tells me that it's convergent. And so if it's convergent, then I know I have a limit. So we want to find the limit as n approaches infinity of the explicit sequence 1 over n. And we know that that is 0. And again, notice that these are the same. So my horizontal asymptote and my limiting value are the same. You could, on your graph, trace this, and as you trace out to the right forever, you can look at your y values, and you can see they're getting smaller, 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 and getting very close to 0. We know that these are never going to become negative, because if my explicit formula is 1 over n, the only way I could get a negative answer is for n to be negative, and if n is getting very, very large, then obviously it's not going to be negative. All right, again, here's a second example. So I have my explicit formula. So once I have the explicit formula, we're going to graph it. So we're going to get this graph here. So again, what we want to look at is, do I appear to have a horizontal asymptote as we move out to the right? Is it becoming almost a constant? Or is it going up forever, down forever, or some sort of chaotic behavior? So again, out to the right here, we seem to be leveling off. So this appears to be approaching a horizontal asymptote of y equals 1. The easiest way to figure out what that value is, again, is to trace out on your function, or remember, you can look at the table value. So remember, if you're trying to determine what this y value would be here of your horizontal asymptote, you have a couple options. We can trace, and as we start to trace here, we can look at the y values. So I'm looking at my y values. So my y values appear to be getting smaller. They appear to be getting closer to 1, but they do not ever seem to be crossing over and becoming less than 1. Your other option would be to look at your table, and here we're just going to put in some really large numbers. So I'm going to start at 100, and then I'm going to try 1,000. 10,000, 100,000, 1 million there. So I just keep on putting larger and larger numbers in, and then you can see that we start to actually get 1. If you come over and look at that number, you can see that it's not actually 1, but that it's being rounded to the value of 1. But that's going to tell us what our limiting value is, and it also tells us what our asymptote is. So we know that this is convergent, and we know that the limit as n approaches infinity of n plus 1 over n is also going to give us 1. So again, my asymptote and my limiting value are the same value. Okay, so again here, this is my explicit formula. So we're going to graph our explicit formula. We're going to get the parabola. So this is going up forever. So I don't have a horizontal asymptote to the right at all. So that tells me then that this is divergent. And then remember, if a sequence is divergent, then my limit as n approaches infinity does not exist. In this case, we could say this is infinity because it is going up forever. So technically we can put the infinity there to let someone know that it is going up forever. All right, and then our last sequence here that we're going to look at is this -1 to the n. So when I graph that, so if I graph -1 to the x, notice you really don't see much on your calculator. This is not a continuous function. You're actually just seeing a couple of dots here. The function actually is giving us this. So our first term is -1, our second term is +1, third term -1, +1, -1, +1, -1, +1, etc. So that is actually what my graph of my function looks like. So the graph is jumping back and forth between the numbers +1 and -1. So this would, again, would be divergent. So my limit as n approaches infinity of -1 to the n, again, it does not exist. So here we can't use like infinity or negative infinity as our answer because it's not going up or down forever. It's jumping back and forth between these two numbers. So the only option we have is to say does not exist. Okay, so I want to just bring back something that we talked about in chapter 2 with our rational functions. So there's actually a way for me to tell with these rational functions. So remember, a rational function is where I have a variable in the denominator. So there's an easy way for me to tell if my limit's going to exist and then whether or not it's convergent or divergent from that information. And remember that that rule comes in using the degree of the numerator and the denominator. So here, if we look at this, the degree of my numerator is 1, and the degree of my denominator is also 1. So remember, when the degree of the numerator and the denominator were the same, then my horizontal asymptote came from these leading coefficients, and that one's going to be a 1. So this tells me that I have a horizontal asymptote at y equals 3. And so if I have a horizontal asymptote, remember that is my limit. So that tells me that I know the limit as n approaches infinity of 3n over n minus 1 is also going to equal 3, which tells me then that I know that this is convergent. So on the second one, the degree of my numerator is 2. The degree of my denominator is 3. If the degree of my numerator was smaller, then that told me that I had a horizontal asymptote at y equals 0. So whenever the numerator degree is smaller, we know it's always y equals 0. So my limit as n approaches infinity of 5n squared over, so my limit as n approaches infinity of 5n squared over n cubed plus 2 is going to equal 0, which again tells me that this is convergent. So this just gives me a little bit of a shortcut to do this instead of having to graph it every time and look at it. And then finally this last one, my degree of my numerator is going to be 3, so highest exponent. The degree of my denominator is going to be 2, so again highest exponent because those are in standard form. If the degree of the numerator is higher, then remember that tells me there's no horizontal asymptote, which is going to tell me that my limit as n approaches infinity, which is going to tell me that my limit as n approaches infinity of this expression, n cubed minus 5n squared over n squared minus n, does not exist. and therefore my sequence is divergent.